Hi, everybody. This is Rollin King coming from St. Paul, Minnesota, where today it was a balmy 30 degrees and sunny. And I would like to take a few minutes to tell you about the current status of the geometry optimizer that I work on, particularly how to use it and some of its new features. Before I forget, I want to give credit to Alex Haida, too, who has done a lot of work on this this year. And in particular, he's worked on a lot of the interfacing of QC schema and QC engine and QC elemental and some of the stuff under the hood that I'm not going to talk about in the rest of the time today. So a little bit of background. The C++ or old version of Optking is still the default Sci4 optimizer at present. So if you run Sci4 optimized SCF, like many of the current Sci4 tests, that's what you're using. And I've been very slow to debug and basically haven't done any development on that code for a long time because I was working on a new one that has taken a long time, but it now duplicates all the capabilities of the old code. It's actively maintained. We got this year a good active test suite going. All the Sci4 tests will run, or almost all, with trivial changes to the input with the new optimizer. A few complex calculations which are probably changing anyway as the driver changes involving Python wrappers or something. Might require a little more work. You can get the code easily on GitHub by cloning it, sticking it in your Python directory. We should update the version in the Sci4 dev channel, Conda channel. There's an old version of Optking, but it's too old. You wouldn't want to use it. The basic default approach hasn't changed. We're focusing on minima. I'm not going to talk more about specific methods. Now, I want to talk about interfacing, how you can use the code, and then some of its new features. All right, so how can you switch over to trying out Optking? I'm going to give an example of Sci API, Cython, and explicit looping. I'm going to change my screen share here. There we go. All right, so for the first example, here's a Sci API, pure Python. Most of this is totally standard. The only thing new is that we now see we have Optking optimized Sci4. So compared to a regular Sci4 API job, you see import Optking, and then from this module, we have Optking optimized Sci4. Optking is going to get the molecule and get its parameters from Sci4 through this wrapper, so you don't have to change anything else about what you do. But it returns a QC schema dictionary. It doesn't return anymore a convergence flag or whatever it was returning before. Instead, it's a complete QC schema dictionary. So just to show you that, you can look at the contents of what's in the returned file. We keep a trajectory. So we've got information about every step in that trajectory, and then everything you would expect to find there. So I printed those out just so we can see. So to run this, just run Python, the pure Python API. Optking is using the Python logger utilities, so its output doesn't go to the standard output file. Here we see what was in the QC schema, so those are just the keys. You'll see an initial molecule and a final molecule and a trajectory. We can see all the normal properties of the next to last geometry, the last one for which a gradient was computed. And all of the QC vars extras that some of you are used to looking at, they're all in there too. Just to show you that everything's in there without printing out the whole dictionary. The log file looks a little different because you'll notice these warnings and info. We also have debug mode so that we can get different kinds of messages. This has just the optimizer output in it, so that's a little bit different as far as where you're used to looking for things, but you can still do the old grep for the tilde. Sorry about that. Grep for the tilde, and if your screen's wide enough, you can see this nice convergence where everything's going down in order of magnitude a step, which is great because it's just water. Okay, now for Cython, So second way to run it is using Cython. So this is more of a traditional Sci input, not strictly Python, because we have these alternative input formats for molecule and for the keywords. This is actually the Sci4 test op1 test case. The only thing I've changed is I've commented out these 3 lines right here. This energy optimize SCF and the compares, and I've replaced them with these. Import Optking, optimize Sci4. And then again, we have to do a little more work to grab the last energy, or in this case, the nuclear repulsion energy from the last step in the trajectory to do our test. And to run this, we're going to run Sci4 so that we get that pre-processing. And otherwise, the output will be identical. You'll get a QC schema output with all of the same information. The third thing I want to show you is new as of a couple of months ago. And this is a new opt helper class, I'm calling it, at least for now, so that you can do explicit looping if you want to with an optimizer. So here's the new class, Optking opt helper. In this case, the computer type is called a user type. And what that means is that the user is going to provide the gradient and the energy. In this case, I'm using a Leonard-Jones energy and gradient, but you could use anything you want, whether a Sci4 method modified or in its original form, or any other method, to get an energy and a gradient, and you assign them, and then you can take a step, you can test convergence, and you can loop. Not all of the features of the optimization algorithms for minima are going to work with this, but the primitive ones where you get a gradient, update the Hessian, take a step, etc., are going to work just fine. And when you close this opt helper object, you get a QC schema output, which will be identical to the other 2 forms. So there's 3 ways to run the optimizer that I showed you: the Sci API, the Cython, and this explicit looping tool. And you could use Optking, of course, without Sci at all, but I'm not going to talk about that explicitly today. I'm going to hop over to my PowerPoint window. Okay, and now I want to talk about the new features that have, before this summer anyway, have never been in Optking before and are not in the old one either. The first is the, okay, a little side note, out-of-plane angles are now working. If you have, I don't like out-of-plane angles, but if you have something very nearly planar, like a formaldehyde that's not quite planar, and the bends start to get redundant, you can have problems. So I think that's fixed for those little cases, but out-of-plane angles now work if you really want them. Okay, bigger things. I added ranged coordinates. So now you can say that you want a distance to be constrained to a range no smaller than, say, 1.3 angstroms and no larger than 1.35 angstroms. It can be anywhere in between, but it won't be allowed to go outside those bounds. And it will try to impose them if the initial geometry doesn't satisfy them. But because there might be internal coordinate displacements involved, that can't be guaranteed to succeed, but usually it would. Here's just an example. You could do the same thing for bends. You could restrict a bend from between 105 to 110 degrees, not outside that range, and you can do multiple bends at the same time. These keywords are non-native to Sci4, which means the Sci4 doesn't know anything about them, so they have to be passed as an extra argument. Otherwise, you can run them just the same as the other 3 ways that I showed you how to use, well, the first 2 ways anyway, to show you how to run Optking. So you can range coordinates. Second thing I want to show you is arbitrary extra forces. So there was a 2017 forum question asking about adding arbitrary extra forces. And there wasn't a good answer at that time. Now, finally, 3 years later, I give a good answer. I don't know if that sets a record for length of time for a good response to a forum request. But here it is. You can take any internal coordinate and you can add an external. You can think of it as extra or external, either way. Here's a Hooke's law force, bond distance, OH bond. This is an arbitrary sort of force constant here, centered around 0.950 angstroms. This would constrain or add an extra force onto both OH bends. You can use arbitrary mathematical functions, but it is processed as a string. So there are currently some limits down here on what functions you can use. If you wanted to dampen the force that you are adding to the bonds, here's how you could do it. You could just add some exponential decays onto both, so you don't get a crazy step if you start far from equilibrium. And so you can have all kinds of fun with extra forces. The last thing I want to talk about is something I've worked on for a long time, but it's finally in a position where you can do some really neat chemistry with these dimer coordinates, I think. So here's the basic idea, and then I'll show you an example. The basic idea was originally conceived at a Cython meeting in Athens years ago, and Wesley Allen wrote up some of the original ideas. If we have two monomers, you could have more than a dimer, but if we want to orient two monomers, we can do that if we have three fixed points assigned to each monomer. We're going to impose the restriction. The only restriction is that each one of our reference points is going to be a linear combination of the atoms of that fragment. So B1 is some linear combination of the atoms on B. So is B2, so is B3, likewise for A1, A2, and A3. And if we have those 6 points, then at most we need a R, tau, 2 thetas, or polar angles, and a couple of phis, and we can orient one fragment relative to the other one. Okay, now we can use these to position fragments very conveniently, and we can also use them to optimize and freeze coordinates. So I'm not going to go through all these now. These are test cases that exist in the Optking test area, so you can look there for examples, or I can discuss them with you directly. But here's some examples of things that I've done. Spin one benzene around above another one at a distance of 6 angstroms. So this is an easy thing to do by hand if the two benzenes are perfectly parallel, granted. But if they were not perfectly parallel, or if you want to spin around a rotational axis, it might be more work. Example 2, methylthiophene tyrosine. Scan the distance between monomers at a fixed orientation. So this is just taking advantage of the machinery to orient two fragments the way you want them, and then just vary a parameter. So this would be single point energy scans, but convenient ways to orient fragments. And then 3, sort of a full featured example where we optimize monomers and the distance between them at a fixed orientation. So here's what that would look like. This is the last slide. So there is a little bit of learning overhead to specify these reference atoms, but then there's a huge payoff for that work. So I've illustrated them over here, how this would work. Methylthiophene, its first reference atom, 1, 3, 4, 6, 8. These are just the ring atoms. So this is going to put the first reference atom right in the middle. If you really wanted a center of mass or something, you can add coefficients or weights for each of the atom, but the default is that they're all equal weighted. So this gets you to the middle of the ring. The next reference atoms are 8 and 11. Don't actually matter as long as they're not in a line. For tyrosine, we list 13 to 18. These are just the ring atoms. So that's a convenient way, no trig required, to give you a reference point right in the middle of the benzene ring. And then you pick a couple of other atoms, 13 and 15. As long as they're not linear with the other reference atoms, probably doesn't matter so much what you pick. And then once you've done this, you can do all kinds of fun things. I give a couple examples. One, a single point scan of RAB. So you can construct a dimer frag object and then use a tool here called orient fragment and give it the internal coordinates that, the inner fragment coordinates that you want. So if you wanted to keep the orientation totally fixed between these two fragments and only vary the distance between the center of the two rings, that's what this code does. It's a little bit hairy how the Cartesian geometry gets returned and then put back into psi to calculate the energy, but it works, and you could do it as well with angles. Okay, and then to the sort of full-featured option here, you can do an optimization of the distance and the fragments without changing the orientation. So you may have noticed this last line, I've selected the 5 angles to be frozen coordinates. So this would take a fragment and another fragment and hold them just so, and then optimize, run optimize or Psi4. And what's going to happen is the separate fragments are going to be relaxed, and the distance between them is going to be relaxed, but the orientation between them is totally fixed. So this kind of capability, the variations are endless, but this kind of capability for constrained bonding situations and active sites in particular, and so I think could be really really exciting to play with. Thank you for your time. Hope we can get good optimization problems from you. It's always more fun to work on an optimizer when someone you know is actually using the capability for something good.